Hi everybody, I'm Asaf Zohar from Similar Group. Originally this talk was supposed to be given by Einat. Unfortunately, she couldn't make it here today, so I'll do my best to cover for her. What I'm going to talk about, our case study is scaling out our website categorization algorithm. But before I'm going to dive into how and why we scale it out, I'm going to give a brief intro to SimilarWeb for those of you that don't know us. So SimilarWeb was founded at 2007. A little bit more than 3 years ago, we launched our SaaS product that provides information about any website on every app in the world. Back then, we were around 20 employees. Today we are already 300 employees. We have 6 offices worldwide, including Tel Aviv, London, New York, and the Bay Area. And without too much of name dropping, you can see some of the customers that use our platform. So what is it that we are doing? So we could provide for any website, either the online or the mobile structure of it, traffic estimation. We say how many people visiting the sites every day, how many pages they are doing, how much time they are engaged within the website, how they get into the website, either directly or from links from either other referring websites. Who are those referring websites? If they're coming from search, which search engine? How much of the search came from organic traffic and how much of it was paid? What were the keywords? How much traffic they're getting from social media? Where they're putting their advertising, who are the publisher websites, who are the ad network that they are working with, what is the industry that the website is working in, a little bit of the interest of the users that are going to these websites, which other websites they are looking at, who are the competitors of these specific websites, and a little bit of the content of the websites. And also for mobile apps, we provide rating, we provide engagement, how many people downloaded the app, how many people opened the app, how many times a day, which days of the week, which hour of the day, retention, meaning how many days after downloading the app the people stay active, and some bunch of metrics from the App Store itself. How we do it? So we have several sources. One of them, we have international panel, actually anonymous data from users that operates within their desktop or their mobile, and we can learn from that how they engage in the digital world. We have a crawler that spans 2.5 billion pages every month and collect information about the technology that the website is using, about links between websites, about the description and the title of the website. We have ISP data, and we have direct measured information from websites that shared it with us, and we can benchmark all our estimation with this data. All of this information is going into a cluster of machines that uses statistical and machine learning algorithms to provide the different KPIs that we are estimating. To run all of this process and provide this data for 60 million domains and 2 million apps every day in 200 different countries, we can say that we are rather big data operation. We digest 90,000 events every second with fresh 4 terabytes of daily compressed data. In the processing, we generate 100 terabytes of I/O every day. We have more than 150 machines in our cluster that runs statistical and machine learning algorithms. And to do all of that, we really fund many open source technologies, including Python and R and Airflow and Docker for orchestration, Hadoop and Spark and Hive and Scala and so forth to run all of this process. So now we can go a little bit of what is the content-based categorization algorithm, and first why we need it. We need it in order to group different websites together, to be able to compare apples to apples. And a user going into our website, into our platform, can immediately understand what the website is about and where it's operating. You can take insights about a specific industry. If you look at the shopping industry in specific country, you can see list of all the websites that operate in this specific industry, who are the most significant players, and to understand how saturated is the market, how well branded are the leaders of the market, and also investigate unknown markets. And some of the examples here is the website of Jaguar, and to know that is about vehicles, and a website that about Iowa corn that is agriculture and forestry, and another website that is dealing about shopping of jewelry on the internet. About the categorization tree, so the categorization tree itself is hierarchical. We have 25 parent categories. Underneath them we have 221 subcategories. All of them more or less preserve the common industry convention, but it was a little bit tweaked to our purposes to best serve our customers. So in overall, we have 246 categories because a general website, for example, a general website about sports will not belong to any of the subcategories underneath it. It will belong to the parent category sports. And we have all kinds of categories that describe the different activities within, or the different websites within the internet. The data that we are using in order to classify these websites based on their content, so we have 500,000 manually categorized websites. Some of them were categorized in-house, others were categorized using crowdsourcing activities, and some others were taken from open repositories where we can benchmark their category and we can also match them one-to-one to our category tree. We have some between 11 to 16 engines that generating features. The features are several tags or common phrases within the website that describe the activity of the websites. And it is 11 to 16 because in the old version, before we scaled up, we can use only 11. And when we scaled up, we could add more features or more engines into the process. We generate around 100,000 different features per engine to get overall 4 million different features to the algorithm. And you can see the features for list of some of the features for the Walmart site. So you can see electronics and home and online shopping and so forth that eventually is supposed to describe what's the industry that this site is operating in. And after training the model and being able to predict, we would like to apply the prediction to 200 million websites that we know that exist in the internet. So before we scaled up, we had a previous algorithm. So let's discuss a little bit about the previous algorithm and understand why we would like to scale up from it. So the previous algorithm was running a few years ago. It was developed a few years ago, and with the technology that we had then, we were a little bit limited. But it was a single machine using multi-threaded application that ran logistic regression that tried to predict in one run any of the 246 different categories. So it was a monster, actually. Very impressive engineering-wise, but still a monster that was highly optimized. And to solve the logistic regression with a matrix of 500,000 different websites and almost the double of the amount of features, it was very tricky, and we had to optimize it. We need to manually tune all the loss functions in the algorithm. We need to aggregate the features from the different engines that generated them. So, and from that to choose only 1 million out of the total 4 million features, which means that per specific engine, it is possible that we lost the most meaningful features in the way. The limitation of it's only scaled up. If we want to add more features, we want to increase the learning set, or we want to tweak the algorithm or run faster, we need better hardware. The pre-combination of the features reduces the coverage of the entire algorithm, and we lost some of the some of the meaningful algorithms for some of the sites. The runtime for training such an algorithm was a few days, which is very long and very difficult to tweak and iterate over the algorithm itself. The code itself, it was very, very complex, and it was very difficult to change the algorithm on the way. And it didn't pass the bus test, meaning that if a bus ran over the engineers that develop it, we will not be able to maintain it. So because of all of these reasons, we would like to scale it up and simplify the algorithm. So the first objective was to maintain or even improve the accuracy that we had till then. We would like to get a much simplified code that we will be able to support it, and we will be able to distribute between the different people in the company. We would like to increase the coverage. The coverage, if we want to predict 200 million websites, the coverage of the previous algorithm was something around 60%. To increase the coverage, we need to add more features, to add more engines. In order to do that, we need something that can be scaled up. We'd like it to be modular, which means that we can add a new engine into the algorithm and easily train it again and without affecting the previous results. And we want it to scale horizontally, meaning adding more computers and not stronger computers in order to run faster or run on more data. So the first idea that we took in order to simplify or scale up the algorithm was to utilize the hierarchy that we had in the categorization tree, meaning that we can learn first only the parent category and afterwards to learn or train a model per parent category to learn the subcategory for the websites. It's immediately enable us to learn everything on parallel. We can train the different models on parallel because we already know what is the parent category of each of the sites that we had in the learning set. So we have one model for the parent category and another 25 models for the subcategory. And actually the learning set or the number of features for the subcategory is smaller, so the models are smaller and it's easier to train. In addition, we used more sophisticated feature selection, and we did it per engine. So we kept the most significant or most informative features per engine. And looking at the data, we realized that actually most of the features there are many duplication in the features, either because they are plural or meaning the same, or they are the same words but in different languages. So we started with translation and lemmatizing of all the features that we have in the database. And then we ran information gain per engine and took the top 200 most informative features per search engine. After collecting the engine, so we get a matrix that looks something like that. We have each row is websites in the learning set, and the columns represent the value of the features that we get per engine of data, and the values could be either Boolean or actual scores. Now, each of these tables goes into multinomial logistic regression. So to learn the parent category, we are running 16 different multinomial logistic regressions. We use the rich penalized, and we even cross-validate in order to optimize the penalty parameter, the lambda, and the optimization was done using coordinate descent because of the data was sparser and smaller than where we begin with in the initial algorithm. So eventually we can get a new matrix where we have again in the rows all the different websites that we have in the learning set. And in the columns, we have per search, per engine that generates the features, the probability to each of the different parent categories. So for each engine, all the categories are summed to 1. And this new matrix can be served as a new set of features in order to eventually understand what is the parent category using ensemble learning. So the ensemble learner that we chose was a random forest. So we have an ensemble of 300 different trees. The input was, as I said, the matrix of the probabilities of the different categories from the multinomial logistic regression, and the output was the prediction of the parent category for each of the websites. And the next step will be to learn what is the subcategory for each website. In the application or the prediction process, not in the training, we predict first the parent category and then goes and applying the specific subcategory for the specific subcategory model. When we are training the model, we can do all this process in parallel. So we have one multinomial with random forest algorithms and random for the parent category, and another 25 models that run to learn the subcategory for each parent category. Each one of them ran 16 different multinomial logistic regressors, so we have in total 25 parent categories times 16 engines, 400 different multinomial logistic regressors that ran and trained during the process. And again, we use the same reach penalty and optimization of the cross-validation parameter and coordinate descent. And we get the same metrics per parent category, per for prediction for the per subcategory, sorry. So each engine provides the probabilities for each subcategory prediction, and everything is summed to 1. And eventually, this also goes into ensemble learner to provide the final estimation. In this case, we use voting instead of random forest. The reason for that is that voting and random forest gave more or less the same results. And because simple is better, we chose voting eventually to give the prediction for the subcategory. The implementation of all this process was done in Spark using Scala, because Spark has out-of-the-box implementation for multinomial logistic regression that can be done distributed. It's a very simple implementation. You can see here with 4 lines you can run multinomial logistic regression in Spark. The other alternative was to have a cluster of different R servers, and we will develop in-house something that will distribute all different training algorithms between the servers in the cluster. But this will be only an ad hoc solution that will not lead us to better, or we cannot utilize it to additional algorithms, and we are planning or started to use Spark in order to implement and learn more complex algorithms in distributed way. So to sum it up, we did hierarchical design that generalize and reduce the overfit. Instead of learning 250 categories at once, we're learning every time smaller amount of different categories, simpler tasks, and reduces the overfitting. The design is modular. We can add a new engine, run a multinomial logistic regressor for it without affecting all the other multinomial logistic regressors of the other engines, and just add it eventually to the ensemble learner. It's parallel and it's horizontally scalable, so we can add more computers to have it run faster. And the implementation is independent, and we can optimize for the penalty for the meta parameters of the algorithm. The eventual results that we improved the accuracy from 76% to 82% at the final algorithm. The algorithm itself is much more simple, and it's when we can hold it and everybody can understand what's going on in there. The calculation itself was reduced from 5 days into 5 hours, just because we can parallelize all the different regressors. The maintenance is simple, and because we were able to add more features and we chose the most valuable features per engine, we could increase the coverage from 60% into 90%. So that is what I have for you today. Thank you very much for listening.